SwayamPrabha. Digital India. Educated India.
Welcome to the Muffler Acoustics course. So, in the last lecture we were discussing about the Helmholtz equation, the one dimensional Helmholtz equation, which is given by the following. Typically, this equation is used to model planar wave propagation in ducts, one dimensional ducts or planar wave propagation, where symbols carry the usual meaning what I explained in my last lecture. Here K naught is omega by C naught is sound speed, P tilde is the acoustic pressure, and x is the coordinate. So, maybe we can consider a duct like this, perhaps so the wave propagation direction is indicated. Of course, other wave propagates in this direction, but the idea is that if we consider the duct section to be circular, it could also be rectangular or square. The idea is over this entire section the pressure value, acoustic pressure value is constant, so is the acoustic velocity, particle velocity along this direction. So, it is basically the phase of the wave is constant over this plane. So, it is also called planar wave fronts. So, that is in this along the if you cut any slice, it has the same properties all throughout that slice. So, basically this equation is then used to model your acoustic wave propagation, where P of course P tilde is function of x, and of course time, which is assumed to vary harmonically, we insist harmonicity. So, basically in the last lecture we figured out that this complete solution consisting of wave that propagates along the positive x direction is given by this in plus j omega t, another form of writing it, and still plus. So, this essentially this term is like the phase. So, we can probably write it in a more cleaner and more probably a slightly better form like this. Clearly, this is forward propagating wave, or the one that propagates in the positive x direction, this is in the negative x direction. All right. So, what do we do after this? Obviously, if you put let us say let us call this equation 2, let us call this as equation 1. If we substitute say this part in equation 1, it will satisfy, and so will the other part. So, they form the complete they form the complete solution or complete basis, because it is the second order differential equation. We need two solutions, and A and B are the arbitrary constants, also known as the amplitude. A and B are the amplitudes of the wave or the progressive wave. So, this is perhaps the first time that I am introducing this term progressive. Why progressive? Let us talk about it. As we probably see from this figure, this the waves they are going in certain direction without getting attenuated or without getting reflected. So, basically this solution, this one talks about the wave that goes along a certain direction without suffering any reflections, and similarly this shows the waves in the opposite direction. So, they are progressive because they constantly travel along a certain direction without suffering reflections. Of course, when reflections are there, then something other happens, what we will get is called a standing wave, and that again will depend on the boundary conditions. We will introduce all those things sequentially, but now that we have got the pressure solution, which I will probably write it down. So, here we have the full solution of the acoustic pressure, which is not x and this thing. All right. So, now if we use our Euler equation for momentum, what do we get? Right. Now, this probably you can see from the lecture number 3 or 4, that is the last 2 lectures when we have linearized this. I must mention one point here, that we are still considering a stationary medium. So, u what you are seeing is not like it is a constant translation, u is something like oscillations about its mean position. So, if you have a particle right here, so it does what it does is like this, it does not do like this, it does like this. So, u is basically a kind of a vibration or the oscillation of the air molecules. So, it pertains to the oscillatory velocity of the particles. So, of course, you can have situations in where you have flow in ducts, where the flow not only is the particles are not only translated in time like this, they also do this. So, basically if you have a duct with flow and you have waves propagating through that, acoustic waves. So, you will see something like this, there is a gradual, there is a net displacement of the particle, it is convected along a certain direction, but the waves with the particles are also oscillating about their mean position. In this case, of course, there is no net displacement, there is no net transport, they are just oscillating. So, it was necessary to first distinguish that case, we are still in a stationary medium. Now, since P is harmonic, that is P of x t is P x e j omega t. So, in that case your u will also be something like that. So, here we have the ordinary derivative. So, what we do is that we write this thing in terms of a wave number and the characteristic impedance what I discussed in my last lecture. So, here you have this thing. So, let me call this as equation number 3. So, now we can plug the solution that we saw in equation 2 or probably this one on the right hand side of equation 3 to get what? We will get rho naught C naught u is equal to minus a into j omega t minus k naught x. So, here there will be minus j k naught plus j k naught like this. Well, what we do is basically first of all cancel out j k naught, we will take j k naught common and put the minus sign inside. So, you will get things like this and a minus here. So, that you get things like this. So, this gets cancelled and the solution u x becomes so then this is the solution for the acoustic particle velocity. All right. So, let us call this as equation number 4. So, you have u, we have p, and what we essentially see here, there are quite a few important things that come out of the solutions given by 3 and 4. 3 is the proper formal solution of the Helmholtz equation, 1D Helmholtz equation, and u is the particle velocity that is found out from the momentum equation, which was combined with the continuity equation. So, once you get u p, you can also automatically get u. It is just a matter of putting the solution for p in the momentum equation and simplifying. So, we get both the solutions. So, the thing to be noted here is the quantity rho naught C naught in the denominator, the one that I am underlining. So, this I was just mentioning a while back and also in the last lecture is a characteristic impedance. So, if you recall from the last lecture, rho naught C naught is something like, assuming the density of air to be 1.2 kg per meter cube multiplied by 343 meter per second, approximately 114 or so kg meter per second. So, as a characteristic impedance is basically, it tells you the impedance or the opposition of to the wave propagation offered by the media. So, let us go back to this equation 4 and also simultaneously recall pressure equation. So, rho naught C naught is the thing that comes in denominator. Now, if you divide by u x, what do we get? We get actually the term rho naught C naught comes in the numerator, you get e to the power minus j k naught x plus b to the power j k naught x and a to the power minus j k naught x and minus b to the power j k naught x. Now, suppose this is a generalized expression for impedance. For the lack of space, I am putting this here. We will use this equation, let us call this equation number 5. Now, suppose if we have a duct, if we have only a unidirectional propagation, that is the wave goes only along the positive x direction like this. So, there is no wave that is going in the backward direction. So, b is 0. If that is the case, the numerator cancels out and what we are essentially left with z naught, which is a constant. Rho naught C naught. So, this is the ratio of the acoustic pressure to the acoustic velocity of the forward propagating wave, that is a progressive wave, all right, and that is given by rho naught C naught, and the value is known. Similarly, if you have a wave that propagates in the negative x direction, it is very easy to see that the ratio then is minus rho naught C naught. So, it depends on the direction in which the wave propagates. We can define a convention, but the important point to be noted is that rho naught C naught is constant. So, it does not depend on the cross section area of the duct, it just depends on the physical properties like the density and sound speed, which also depends on the temperature. So, it is independent of the or the geometry or the physical dimensions of the duct. So, it is called characteristic because it is very inherent to that medium, inherent to air, which is the medium in which the acoustic waves are propagating. We need to know this physical constant. So, that is why it is called the characteristic impedance rho naught C naught of the medium. However, there are other things also which will be particularly useful in the context of muffler acoustics, that is basically when we are considering system of ducts. Mufflers are nothing but basically, let me draw some typical muffler configuration. So, you see this inlet port, outlet port, here inside it could be a complicated things. What we are, I am just trying to give you a glimpse, a sneak peek into what you can expect in the later part of the course. You can have a simple expansion chamber or something like with perforates, something like this. There could be flow here, uniform plug flow and all that. There could be neck extensions forming quarter wave resonators at the inlet outlet. There could be a lining here, there could be lining. This shape could be more complicated rather than a circle, and you could have actually multiple such things. You can have more resonator cavities and you can make the structure as complicated as you want. We will of course begin with very simple systems, and you can have temperature gradients. The point is, it is all a study of how to manipulate wave propagation within a ducted system to reflect the acoustic power back or to absorb it. Those form the those constitute the principles of muffler acoustics, and we are going to discuss all that in due course. But for now, coming back to the fundamental equation, let me call this equation number 6. So, it is important to define a couple of other impedance parameters. So, we saw u x, which is the particle velocity, but now if we consider this thing, this has certain area. Let us say d is the diameter and S p or the area of the port, inlet outlet port area is the diameter is same. So, S p is the diameter. So, what is the volume velocity? So, if you multiply u x with the constant cross section area, what do you get? We actually get things like volume velocity. So, u x into S. So, if we basically divide this z naught, if you multiply the denominator of equation number 6 by S p. So, P x divided by S p into u x, we will get something like rho naught C naught divided by S p. So, this is also the characteristic impedance, but this takes into account the cross section area of the inlet port or of a duct in general, that is the dimension of the duct. Typically, we will write this as rho naught times y, let us say y naught, where y naught is C naught by S p. We will name this particular thing in due course, but this is called the characteristic impedance in terms of the volume velocity. So, let me call it Z v, volume velocity for the waves that propagates along a certain direction, and we have yet another quantity called the mass velocity. So, mass velocity is nothing but let us say V x is rho naught times S p into u x, that is volume velocity meter cube by second and kg by meter cube. So, what you get is kg by second. So, the reason that I am introducing this quantity, and as is conventionally used in muffler acoustics, duct acoustics, is that typically the mass flow remains constant. When you multiply by density, density might be at the upstream part, it might be the air is hotter. So, it is a lighter thing. So, density is relatively lower compared to the density at the downstream, but what essentially remains constant. So, the volume velocity might fluctuate, but mass velocity is always constant. So, people do work in terms of mass velocity. As a result, what happens is that if you just consider this equation and divide, let us say p by u, we divided initially this, multiplied this by S p. Now, if we also multiply this by rho naught, we essentially get this thing. So, P x by V x is what? It's basically rho naught comes here, S p also comes here. So, we are eventually left with y naught, what we defined in the last slide. So, y naught is just like bringing this thing, this particular thing here in the denominator. So, basically z mass velocity is given by y naught, which is nothing but sound speed divided by the cross section area of the duct. So, this takes into account the dimensions of the duct, of course, and it is regardless of the density and considers only sound speed. So, obviously, for a duct with a smaller dimension, smaller diameter, characteristic impedance is more, and vice versa for a larger duct. So, a smaller duct has more impedance towards or it offers more opposition to the propagation of acoustic waves, and we will see that the moment we use things like this sudden expansion that is happening here partly, or maybe things like this, the impedance of this port and this port, while they are same, the characteristic impedance of this part is vastly different from this one. So, this will be one of the reasons why a lot of acoustic power is reflected back into the system, and why that attenuation is being produced. But it is important to see this part C naught by S p, which is the characteristic impedance, and with this I think we will conclude our discussion for this week's lecture. In the next week we will probably discuss about resonances in the one dimensional system for a closed end pipe, for an open end pipe, some simple solutions that we can see when you have piston excitation at one end and open or closed end at the other things, before we move on to something like including mean flow effects in a duct. So, these 2 or 3 topics perhaps are important before we go into other things. Thanks a lot.